Hi, everyone. Welcome to the second session of the EDAM Summer Series. For those of you who were with us yesterday, thank you for joining again. And for those of you who are joining for the first time, welcome. And just a brief introduction about what the series is and about what EDAM is. So EDAM is the Ethiopian Data Analytics and Modeling Consortium. We're sort of working over a few pillars, but a big pillar of what we want to do is based on capacity building. And this lecture series sort of falls within that. This initial trial that we're starting, just to see, how the reach of what we're doing works and whether it's something that people are interested in. There'll be a feedback form at the end. So please do, let us know if you've enjoyed the session and if you have any sort of suggestions of what to do or what you'd want to look at afterwards. Just a few housekeeping rules before we start. So microphones and cameras are disabled for the session, but the chat feature is enabled, and we'll be monitoring the chat throughout. So if you have anything that you'd like to raise that isn't a question, please post it there. But can we please ask that you don't use the chat to introduce yourself, just so that we can keep it sort of open and easy to spot if there are any issues. If you do have a question, there's a Q&A feature, so please use that to ask any questions you have. And if someone's asked a question that you want answered, please upvote it rather than asking it again. There also may be an option to navigate the slides yourselves. If you do see that option pop up on your screen, then please select sync to the presenter option. And then when we've advertised this course, there was an option when we advertised this course, you would have seen that you'll receive a certificate, but you'll only receive the certificate if you stay for the full session and complete the feedback form, which includes a short quiz on the content covered. And then finally, please note that the session will be recorded and that the session along with the slides will be shared with your certificate. So we are sharing the slides and the recording. Perfect. So again, just to mention, please don't introduce yourself in the chat, just so that we can keep it clean. And with that, I'll get started with our session. Just one second. So everyone should be able to see our slides. So everyone should be able to see our slides. I see a thumbs up, so I'm going to get started. So the session today is about whether artificial intelligence can emulate human intelligence. And with the introduction of Claude into Ethiopia, we're also going to cover some agentic tools. Sorry, I'm just trying to get all the tech working. And so Gina and I today are going to be presenting the session. We're going to split the presentation of the session across a few sections. But really what the session sort of started out from was earlier this year, the consortium sent out a feedback form. And one of the questions was, what is AI? And there were a whole host of answers that sort of came back to this. And, a lot of them sort of compared them to human intelligence. And it's not specifically related to people who've completed the form. We find that it's quite widespread when you ask people what is artificial intelligence. And given the recent boom in AI and all the buzzwords that come with it, it's been really hard to make sense of it all. So today, what we want to chat to you about is a few things. So it's what is AI? How is AI used? How close is this to human intelligence? And also, what are the costs of AI? And then the final sort of tag on that we're going to chat about is what is agentic AI? And our session today is really about demystifying AI. What we'd like you to walk away at the end of the session is an understanding of what it is and what it isn't. And very importantly, we also want you to, while it is something to be excited about, we want you to walk away being aware of some of the costs and considerations. And we want to highlight why it's important that we need a democratized contribution to advances in the AI space. And so with that, let's get started. So we're going to start with sort of the most simple and basic question, and that is of the whole session. But it turns out to be one that's surprisingly hard to answer, and that is, what actually is AI? So in this section, we're going to talk about 4 different types of intelligences. The first is human intelligence, which we'll discuss in more detail in the next slide. But as you'll see throughout the session, this is what machines are based on, but can't really match. And then the next 3 terms, which you can see on the right, all relate to machines. and I've grouped them together as machine intelligence. And these terms are artificial intelligence, artificial general intelligence, and artificial superintelligence. And the concept of these terms are often used interchangeably, and this is what causes a lot of confusion, and also consequently a lot of the hype, and it's hard to know where we really stand. So over the next few slides, let's try and get to the bottom of what each of these actually is. So at the start of the session, I said it was difficult to answer what AI is. The surprising question is that it's the same for human intelligence. There's really no agreed definition, but they do have some aspects in common. And so you'll see two definitions on the screen. The first one's by psychologist Roberta Collum, but I think that I think captures the gist of many of these definitions quite well. And so this definition is that intelligence, and by intelligence we mean human intelligence, can be defined as a general mental ability for reasoning, problem solving, and learning. It integrates cognitive functions such as perception, attention, memory, language, or planning. And so again, there's a whole lot to this, but really what it boils down to is captured in the second definition, at least in my opinion. And this is what you use when you don't know what to do. And so those sort of capture one specific type of intelligence, which I guess you could define as logical intelligence. There are also other sort of psychologists that have tried to break it down into other independent parts. So you can see one view of this on the right. A psychologist named Gardner tried to split this into sort of 8 different types of intelligence. Others have also argued for broader categories like emotional and social intelligence alongside the logical kind. So again, the main point of this is you can see that there's no sort of agreement of what exactly intelligence is. And so in addition to this sort of lack of agreement on what it is, there's no agreement on how to measure it. And one of the reasons for this is that intelligence is difficult to measure is because it's latent. And so what this means is it's something that we don't observe directly. We only observe its manifestations. And so to try and measure this, people have approached it from different angles. Some have studied it through psychology and social sciences. And a common example here is IQ, which measures the sort of logical intelligence that we've been discussing. However, this is quite flawed, and Gina's going to chat about this a bit more when she gets to her section. Other fields, such as neuroscience, have also sought to explain this more mechanistically through how the brain works. And this sort of understanding of how the brain works is really what led to what we call artificial intelligence today. So the study of the brain led to researchers trying to emulate similar processes in machines. And so again, we have sort of 2 definitions here. The first definition is by John McCarthy, that a colleague showed me that I think captures what artificial intelligence is quite well. And that definition is that artificial intelligence is the science and engineering of making intelligent machines, especially intelligent computer programs. It's related to the similar task of using computers to understand human intelligence, but it does not have to confine itself to methods that are biologically observable. And there's sort of a key part here that I was initially confused by that I think is worth explaining a bit more, and that's that these machines do not have to confine themselves to things that are biologically observable. So while human biology may have been the inspiration behind AI, AI is not necessarily restricted to copying things biologically. In other words, they don't need to copy how a human brain works. And machines can achieve intelligence by any means necessary. So just as an example to make this sort of more tangible, is a plane and a bird can both fly, but they do so in completely different ways. And really this boils down in simple terms, in my opinion, to making machines that can perform a task which require human intelligence without needing to copy how a real brain works to get there. And so one thing to highlight, I sort of gave a quote or a definition of what AI is. And one thing to highlight is that AI is not new. This term was coined as far back as 1995 by John McCarthy, whose definition I read. And the image on the right sort of shows the progress that's been made over time. And also, by extension, shows that researchers have been working on AI for a long time. Like I said, the slides are going to be shared, so I'm not going to go through this in detail, but there's some really pivotal moments in AI highlighted on the slide, going as far back as 1943. What's worth highlighting about this sort of timeline is that this is not the first time there's sort of been a hype bubble around AI. And all the previous times there has been this hype bubble, it sort of burst into what people call AI winters. And again, Gina's going to sort of chat about this more once she gets to her sections. And to contrast what we're going to discuss in the next two slides, it's sometimes helpful to think of simple AI as ANI, which is artificial narrow intelligence. And this was a term coined by Google precisely for this purpose of helping to distinguish the differences. And so what ANI sort of captures is that it's designed to solve a specific task. And narrow is really the key word here. These systems are doing what they were trained to do. And it's very, very important to highlight that ANI does not equal human intelligence. So that might lead you to thinking or sort of asking the question is there a term for AI that matches human intelligence? And the answer is yes, it's AGI, which is artificial general intelligence. And this is the term that often gets confused with AI, and especially lately, this is the term that's sort of led to a lot of confusion, or at least these concepts are mixed up. So the key component of AGI is it's something that can self-improve and generalize to tasks that it wasn't trained for. So roughly speaking, AGI is equal to the intelligence of a single human. And so recent advances in AI may be superhuman. So we know there's sort of some aspects of AIs that are superhuman, but the main component of this is that they're narrow. So you might think of sort of Claude as being superhuman in some aspects or better than us in some aspects, but they're sort of good on very narrow tasks. Some of the confusion around AI or AGI traces back to the Turing test, and it's just worth highlighting or spending a few seconds on. So back in 1950, Alan Turing, who's a computer scientist, asked a narrow question, and that's whether a machine's conversations could be mistaken for a human's. And somewhere along the way, a yes to that question got treated as proof as proof that we had reached AGI. So you can sort of see how LLMs in particular feed that narrative. But answering that question, and again, that narrow question, while appropriate for its time, doesn't constitute general intelligence. And let's also remember what we discussed on the previous slides, is we don't actually know how to measure human intelligence. So declaring that a machine has achieved it is quite difficult. So I won't go over the definition on this slide, but in simple terms, what you should really take away is that AGI is a machine that can think and learn across almost any task. And it's a goal that researchers are working towards, not something that exists today. Okay, and so the final term, which is relatively new, is artificial superintelligence. And so I mentioned on the previous slide that some systems are superhuman at certain tasks. So we thought of Claude, maybe it could be better than us at some tasks. And so these advanced have got researchers to hypothesize a new term called artificial superintelligence. And so these are systems that would be superhuman at everything, where superhuman here is assumed to be better than a collection of experts. And so it's similar, it's sort of a superhuman artificial general intelligence. But very importantly, similar to AGI, this is hypothetical. And so really the simple term and simple takeaway from what artificial superintelligence is that it's a system smarter than entire teams of the best human experts at the sort of task at almost everything. Cool. And so the main takeaway across this entire section is that there's different types of human intelligence, but the intelligence you use today is artificial narrow intelligence, and it does not compare to human intelligence, at least not yet. So now that we've drawn a clear line around what AI actually is, let's look at where it shows up. AI isn't just one technology, it's an umbrella over quite distinct subfields, each suited to different problems. And so I have 4 popular subfields on the screen here, but it's important to highlight that this list isn't exhaustive. So starting with the sort of square on the right, we'll see the first subfield, which is computer vision. And this relates to models which interpret images and videos. So think of things like Face ID, medical imaging, and self-driving cars. Second on the right, you'll see robotics. And so this deals with things like physical sensing and taking action. So think of Boston Dynamics warehouse robots, and also things like sort of small robots used when you do medical surgeries. What's also important to highlight is that there's sort of synergy across these fields, and especially for robotics. So robotics would also use things like computer vision and reinforcement learning, which I'll get to. The next square on the bottom left is natural language processing. So this deals mostly with humans processing human language. And this is what powers large language models like ChatGPT and Claude. And then the final square on the right is reinforcement learning. And this really finds optimal actions through trial, error, and reward. And so there was a system, and there's a documentary on this, which is quite interesting to watch if you have the time, called AlphaGo. And it was about a system that learned to play and beat the best Go player in the world at the time. So as I mentioned, these aren't just this isn't an exhaustive list, and there are sort of other options that you can, or sort of other subfields of AI that exist. So an example are recommendation systems, and then also predictive modeling. And these sort of sit alongside these. But in practice, all of these get used together. And so we'll look at a few examples on the next slide. So on this slide, you can sort of see a range of healthcare applications, which I'm not going to go through in too much detail. Like I said, I'll share the slides, and I've hyperlinked each paper or each description of what these projects are. But in these healthcare applications, everything that we've seen on the previous slide has sort of been combined to come up with complete systems. So on the starting on the top left, you can see a sort of wave passing through a brain. And this is related to a recent project by Meta that was trying to decode sentences from brain recordings. On the bottom left, you can see a sort of screening or a GIF of screening. And this is related to a system developed by Google that's used to screen or to assist with screening breast cancer. On the right, you can see these sort of weird shapes rotating around. And this was based on a project where researchers used reinforcement learning to try and predict protein structures. And the system was called AlphaFold. And it's very interesting because this project was actually one that saw the first Nobel Prize awarded for work related to AI solving a scientific problem. And sort of why this is important, it is that it's sort of a yardstick of how far AI has come. We have AI systems solving problems that have been long-standing and are worth sort of awarding. And then on the right, we have a breakdown of further potential applications of AI. It's from a nutrition aspect. I'm not going to dive into too much detail, but the main thing to highlight is that there's a whole host of applications. And sorry, just to mention, it's a perspective of AI in public health specifically. And these are type of things that we want to start sort of working towards and looking towards and seeing how can we embed AI in each of these sort of subfields. Okay. So as a quick aside is I've sort of showed these applications and they all are quite impressive. But why, how have we gotten here? Why are these sort of narrow systems that we're working with so much better? And so two very quick, perhaps slightly boring reasons is one, that we have exponentially more compute. So in both, on the right, you'll see the number of transistors per microprocessor, and on the right, you'll see the number of GPUs operations per second. You don't have to get into these in too much detail, but what's important to highlight is that both are on the log scale. So the main takeaway here is that there's exponential growth in computational power. Similarly, the sort of second reason, and this is similar to the previous slides that I've shown, is we have two graphs here. On the left, it shows the number of images used to train a vision model, and on the right, it shows the number of tokens used to train a language model. And what you can see here, and the main takeaway, is that there's exponentially more data that's been used to train systems and available to train systems. What is important to highlight is that there's a cost to these, which again, Gina will comment on in her section. So now sort of a pivot. We've said that the session was about demystifying AI. So we've seen some applications and we know how they've gotten there. So we said that there's more compute and more data. But you might be wondering, are the underlying methods that get used a lot more advanced? And the answer is yes, there have been advances in the methods that are used, and these have contributed, but these aren't the sort of main drivers of the change. And the underlying mechanisms that we see are actually quite simple. So I'd like to end this section with an explanation of one of the most popular uses of AI, which is large language models. And I want to show that the underlying mechanism is much simpler than the output makes it feel. And so understanding this will also help with some of the arguments I've made about AI being narrow. So to start with, large language models, when people discuss them, you'll often hear this term tokens. And what a token really is, for simplicity's sake, it's the language that LLMs communicate in. And you can think of them as words, if that's simpler, or sort of parts of words. And what an LLM really is next token prediction. So all an LLM is trying to do is figure out this next unit of speech. So how does it get there? Well, you feed it a massive amount of text, so books, articles, web pages, and then it finds the statistical patterns of how words follow one another. And these patterns become a model that one of these tokens at a time predicts what's statistically most likely to come next. What's important to highlight here is that context matter. The data that they're trained on influences the patterns that they learn. Often these models will be trained in general on like huge amounts of data. But if you want to then push this model to a particular domain, you may need to fine tune it by showing it data, which will tweak the patterns it's learned and make output and sort of make different output more probable. So as an example, if you want to adjust an LLM towards healthcare, you may want to show it more healthcare data so the patterns it learns are related to healthcare specifically. But again, sort of always caveating with we need to consider sort of the implications of what we're doing. These LLMs will be biased and have the same biases as the data that they're trained on, which again, Gina will chat about in her section. So to better understand this, let's look at an example of next token prediction. I know I've sort of said a lot and it's quite hard to understand what someone just explaining. So let's see an example of this in action. On the next slide, I'm going to show you a GIF of a meta system called Llama 3.2 trying to predict the next token. So you should see the GIF starting to play. Here, the system's been asked, who are you? And you can see sort of step by step, what it's trying to do is determine what's the most probable output here. And it picks from a score of candidates that have been generated based on the training data it's seen. So each token will have a probability, and the system just needs to pick the highest scoring one. It's purely pattern completion, albeit very advanced pattern completion. So I hope that sort of, again, I think on the previous slide, I said it's a very short crash course introduction into LLMs. The main takeaway here is it's a simple mechanism. And ultimately, the main takeaway from this section is that AI isn't one thing. It's a collection of subfields solving very different problems. And at their core, the methods we use are quite simple. The ingenuity is in how in the applications that sort of stem from them, and how these AI systems are really embedded in solving human tasks. So I'm now going to hand over to Gina, who's going to do a deeper dive into sort of everything I've been mentioning that Gina will chat about, which is how close is AI to human intelligence and what are the costs of human intelligence?
Thanks, Tristan. So good morning, everyone. My background is sort of more in the biology side of things. So today I'm going to be talking a little bit more about sort of how close is AI to human intelligence, and more specifically talking about sort of the brain and what kind of power we have, and hopefully making us feel a little bit better about our own intelligence when we think that ChatGPT is so much smarter than we are. So the human brain has around 86 billion neurons and roughly 100 trillion connections between them, meaning that the brain has about 50 or 60 times more synapses than ChatGPT has parameters. So even at the structural level, the brain is far superior than most of these sort of LLMs that we use on a daily basis. Although a lot of AI companies don't actually disclose the number of parameters that their model is trained to, ChatGPT 4 is one of the only ones that actually does. Critically, something also to note is that we still don't have a complete wiring diagram of the human brain. we only actually have them for sort of more simple animals like fruit flies that have much more simple brains. And one of the reasons for that is because of the complexity of the human brain and how incredibly difficult it is to fully map human brains. And one of the reasons for that is also because of the heterogeneity from brain to brain. Whereas AI models, their full connectome, so its architecture and all its parameters are fully known and fixed once trained. So we know exactly what is in any kind of AI model from the get-go, and that doesn't change. The biological brain, by contrast, is never static. It's constantly rewiring itself based upon experience, based upon injury, based upon the time of what time of our life that we are in and what things that we need at that point. And this is unique between humans. And you can see this in sort of vast differences that we see in sort of like human brains. So, for example, childhood development is a time where we really see that heterogeneity from brain to brain. One child could be up and walking by 7 or 8 months old, whereas some children are still sort of wobbling at a, sort of like the 1.5 year mark. And that is all considered normal. Also, we see this in brain injuries as well. Two people can have a brain injury and have a hemorrhage in the exact same part of their brain that governs the exact same function, but one person can have much more severe or even different sort of consequences to their brain injury as the other person. And recovery is incredibly difficult to project for human brains because the way that it gets injured and the way that it repairs is so unique from person to person. So most people that are making this sort of AI versus human brain comparison, a lot of the time are coming from the computer science field and not the neuroscience or psychology field. So the comparisons really often flatten out what intelligence actually is. The book Emotional, I'm going to talk about lots of different books today, and I recommend people read all of them because they're all fantastic books. I couldn't recommend them anymore. But this book here called Emotional, it points out that human intelligence develops through lived experience, emotion, and feeling, not just computation. So a lot of our intelligence is unique because it's based on our experiences as a human being. And feelings are something that AI just doesn't possess. They don't have the ability to sort of just decide not or to do something because it just doesn't feel right or does feel right. And that's something that we inherently know as human beings. Sometimes we make decisions in our life because it just feels right. And a lot of that is based upon our unique experiences. And that's something that AI does not possess and is never going to be able to possess. Our main tool for measuring intelligence is also deeply flawed, and it has very deep and concerning, sort of well-documented, very racist roots. So our main way of measuring intelligence is actually the IQ test. But the IQ test was developed out of the eugenics movement that was essentially trying to prove white supremacy, which obviously that can't be proved because it's not true. But yet that is still our main metric of intelligence. And so, of course, deeply flawed because it was developed to prove something that could never be proven. So something else I'm going to bring in here and something that was introduced by Melanie Mitchell is this idea of the barrier of meaning. So AI is basically pattern matching without understanding. And that's something I will sort of come back to over these next sort of like 2 or 3 slides, is basically what AI is doing is it's understanding, as Tristan said, sort of next token prediction. It's understanding sort of what you can see there in the cover of that book, which is sort of like the shades of different pixels, which is what forms the sort of like meaning part of things like computer vision, but it doesn't understand what these things actually are. However, it can fool us. It can look incredibly intelligent. And one of the reasons for this is something called emergent behavior. And this has occurred, and we have seen this, particularly in large language models. And a part of this is because if you train your model on enough data, then basically it starts to display abilities that it wasn't explicitly trained on. But this is simply a matter of scale. It's not the same as actually understanding what's going on. And some of the emergent behaviors that we've seen in LLMs, let's say, are the fact that it's multilingual. That was never something that we intended to happen, but it's something that's happened because we've just shown it so much text. And another thing that we've shown it that it sort of appears very well to do is reason. However, I'm going to come back to the fact sort of how it's actually not reasoning, but is very good at making it look like it can reason. But AI really has no capacity to hypothesize or think outside the box. AI only has the capacity to learn what we have told it. So it can't sort of sometimes when we sit, okay, and we're presented with a problem, we think about how we're going to solve this problem. What we do is we play out different scenarios in our brain. We conceptualize how these things might work. AI does not possess the ability to do that, and it's not going to be able to, or it's incredibly unlikely it will ever be able to. So another concept just to cover here is the Moravec, which I'm never really sure if I'm pronouncing that right, but I'm going to say Moravec's paradox, which is basically a paradox that was suggested, a relatively long time ago, pretty much since the conception of AI, which is that things that humans find the hardest, so things like advanced mathematics, AI can do that really easily. And things that we find effortless, for example, walking on uneven ground, AI struggles with. And this is a paradox that comes up time and time again because it seems so weird, right? Why is it so good at something like complex mathematics? But then if you put AI into robotics and you try and make that robot walk on an uneven ground, it's always falling over. And a lot of the reason for that is because our lived experiences give us an ability to judge based on common sense. And that's, again, something that AI is not able to do. We don't need to have seen a sort of a wobbly pavement in the past to know how to not trip over it, because we can use just common sense to know that, if I don't lift my foot enough over this wobbly paving stone, then I'm going to fall over. But AI can't do that unless it's seen that exact pavement and that exact paving stone in the past. And so here I'm going to give you kind of two examples of, and sort of try to demystify here what appears to be incredible intelligence, but actually is actually quite simple what it's doing. So the first one, like I said, is reasoning. So when we say something to ChatGPT or Claude and we say, we sort of ask it to explain something to us, as I said, what it appears to be doing is reasoning. But actually what it's learned to do is recognize patterns in the way that we've written down our reasoning. So basically, it's just learned to regurgitate text of reasoning that we've written down. It doesn't actually possess the ability to do that itself. And then another one would be computer vision. So as I said from the previous slide, where you can see there, so what you can see on the cover of that book is a convolutional neural network. And what that neural network is learning is it's learning how different shades of pixels, when you put them all together, it's learned how to categorize them. So it can say, that's a cat, but it doesn't actually know what a cat is. It's just been taught that when you put all those pixels together of different shades, that's a cat. But obviously it also gets that wrong quite a bit of the time as well. So now I'm just going to talk a little bit about the hidden costs of AI, because I think sometimes we like to talk about things like clouds and stuff like that when we talk about computers, and it makes it sound like there are sort of no costs for this and it's something that sort of just goes on somewhere else and it kind of like isn't affecting people or the environment. But of course it is, and there are costs of it. So first of all, I'm going to cover the financial costs of it. First of all, AI is obviously a huge business and people have very heavily vested interests in its own hype. Those who have the vested interests are often also more likely to be the AI doomsdayers. So the ones that, come on TV and say AI is going to kill us all. They go on the podcasts and they make their big claims about how, AI is going to be the end. These are often the people that have the most money invested in it. And the reason for that is because if you tell a government, I've made a tool that's going to kill everybody, but don't worry, I have the solution, that gives you an awful lot of power. And that is, unfortunately, what some people are after. And so these people are also creating predictive tools that are being deployed at scale with very little accountability or accuracy. So one of the reasons that people can make claims like, doomsday claims is because the fact that there's very little accountability and they don't have to disclose things like accuracy and training and testing performance. A lot of that just isn't published and they don't have to publish it. So a big problem with this is the fact that we know some of these tools don't perform very well, despite the fact that they're being rolled out at scale. And AI is now dominating the stock market. And that's incredibly concerning when we know that some of these tools don't work and we know that there is hype. And the Intramonetary Fund has recently published a number of warnings about this because AI businesses and AI companies now roughly equate to about a third of the S&P 500's value. And there have been many parallels drawn between this and the dot-com bubble burst, which happened in the late 90s, early 2000s, which led to a global recession. With the invention of the internet, there was all this hype. People said that, it was going to change the world. And of course, we made huge strides, but there wasn't anywhere near the strides that we made that people hyped up that was going to happen. People flooded money into internet-based companies. And then, of course, they didn't pan out. There was hype, there was lies, and those companies massively devalued almost overnight, and we led to a global recession. And there have been a number of parallels drawn between AI and the dot-com bubble burst, and how this could have a profound impact on the financial sector and also on a possible global recession going forward. So just to talk a little bit about the human costs as well. So automation always hides a lot of human labor. Nothing is ever truly automated, and a human has always had to be involved somewhere. One of the ways that we see this is with something like Amazon's Mechanical Turk, which was basically a platform where people were paid very poor salaries, often in low and middle income countries, to do a lot of the monotonous work that is needed to create the ground truth data that actually trains these systems that are in place. Because at the end of the day, AI, as I said, it can only learn what we've told it, and we have to create a ground truth for it to learn from, and someone has to do that. AI can't do that itself. We have to do that. And that work obviously is something that people don't want to do, and AI companies want to do as cheaply as possible. And that obviously has led to a number of issues. And we've seen this in ImageNet. So this is the largest database of images that is currently available that AI models and computer vision is being trained off. And this catalog of images, there are millions of images on this. They include everything, including a number of things that no person would ever want to sit and click through images of. And the people that categorize these images in often sort of like low income settings with very poor working conditions were never offered any psychological support or help for the things that they saw while categorizing ImageNet images. So then to look at the environmental costs, and I'm really going to sort of structure this into three different categories. So the first one is mining. All of this sort of infrastructure, a lot of the time needs a lot of precious metals and minerals, and these often come from Central Africa. So we see that 60% of the world's cobalt, which is a mineral that we need for a lot of computer infrastructure, comes from the DRC. And it's mined through not very nice practices for Congolese people. And also mining in itself is a very environmentally destructive industry. Then also to move on to energy. So we have a tendency to build data centers and supercomputers in very hot, dry places. The 10 biggest supercomputers in the world, except one, are built either in California, Spain, or Italy. So in very hot, scarce regions. So a terrible place to build them. Despite this, energy demand for them is growing at 12% per year. And now US data centers account just in the US for Pakistan's entire annual electricity demand. So huge amounts. And it isn't just sort of the large scale infrastructure that's an issue. We also see that ChatGPT's 2.5 billion queries a day roughly equates to the annual electricity use of 29,000 US homes, which is unbelievable when you think about also US homes tend to be the most energy hungry and the biggest energy consumers of any other nation. Also, for all of these data centers and supercomputers, cooling is a huge issue. It's one of the biggest reasons that energy, it uses so much energy, but also for cooling, you need water. And that's also something that we're incredibly limited, that we have only a limited supply of, and something that we are limited up with as a planet and as a population. One NSA data center in the United States is currently using 6.4 billion liters of water a day. So that's just one data center. So we think of all the other data centers that are out there in every other country. That's an unbelievable amount of water that we could be using for other things. So finally, the last thing I'm going to talk about is the ethical costs. And obviously, most of the things that I've already stated are ethical costs. So I'm more just going to sort of present a few more here. One of the big issues with the way that a lot of these big models have been created and a lot of them have been trained, they've been trained on and for white, wealthy, Western, male, able-bodied people. So they've been trained and created by people that live in Silicon Valley, which is a very, very unique and small subset of the global population and is by no means representative of the global population. And we see this in how they perform. So we know that computer vision now is being used in medical diagnostics. And an issue for this is the fact fact that this has almost exclusively been trained on white skin. And so we know that it massively underperforms on darker skin tones, and it may then further put people of color at risk for things like skin cancer, because if we use computer vision to diagnose them, they're going to end up getting missed. We also see this in AI policing systems that are being rolled out, which is a huge issue because we know predictive AI isn't very good, but yet it is being rolled out currently in policing systems. And we know that, again, those of African descent are far more likely to be categorized as criminals through these systems than white people. Models are intrinsically biased, and they have deeply sexist and racist assumptions that they make. And a lot of this is based on what they've been trained on and the fact that the internet, unfortunately, can be a not very nice place. And finally, something I'm going to leave you with is ImageNet. The writer of one of the books that I presented here created something called ImageNet Roulette, where you could import your picture onto ImageNet and see how it classified you. And so the person I've included here is someone called Julia Wong, and I'm including her because she gave her consent for her image to be shared. She wrote a Guardian article about this, and ImageNet classified her using very racist and derogatory terms for people of East Asian descent, and that's how it categorized her. And you see this time and time again with ImageNet classifications. And so I think what's really important here, and something that I want to leave you with, is people that aren't in Europe and sort of aren't in North America. It's really important that people in other cultures and other countries are a part of the current AI revolution that we're seeing to try and address some of these real structural challenges. It's really important that we really diversify the AI workforce so we can try and address some of these ethical issues. And now I'm going to pass back to Tristan, who's going to do a little bit on agentic AI.
Thanks, Gina. It's super interesting to hear about sort of all the costs and ethical considerations with AI. I'm going to, like Gina said, just quickly chat about what is agentic AI. I can see there's a few questions in the Q&A section too, so I'm going to go through this relatively quickly so that we have time to sort of answer all the questions. So this really is a bit of, I guess, bonus content, and I suppose especially relevant given Claude's rollout in Ethiopia that we mentioned. Agentic AI is sort of the buzzword of the year at the moment, but it's really answering what agentic AI is really a difficult question that I find myself also trying to make sense or having trouble make sense of, given how rapidly the field's evolving. So again, as before, the goal with this section is just to demystify what is agentic AI. So when people mention it, you know what it is. And so before I dive into agentic AI, I just want to position it next to generative AI, sort of position where generative AI fits into this, because it's another popular term that gets sometimes discussed alongside agentic AI. And in a sense, agentic AI is sort of an extension of generative AI. So generative AI is focused on generating content based on human prompts. Agentic AI takes this a bit further and is focused on taking actions. So the main thing with agentic AI, when people talk about it, it's something that can act. So I'm not going to read the definition in the interest of time, but the main sort of takeaway from it is that it's agentic AI is something that can set goals, plan, and execute a task with minimal human intervention. Something that's important to also flag is that you'll hear the term AI agents being thrown around sort of in tandem when people chat about agentic AI. AI agents are a component of agentic AI. Agentic AI is the umbrella term that's used to discuss everything. It's also worth flagging that agentic-based models have existed in other fields for decades. Gina spoke about these yesterday in her session, but the way we use sort of agents or agentic AI is slightly different from how these agents are used in infectious disease modeling. There are parallels though. So what is an AI agent? An AI agent is the building block of agentic AI. And a single agent is just sort of three components bolted together. Again, as I mentioned with the LLM slide, and as you've been hearing through the session, most of the mechanisms and things we use are quite simple at its base, and agentic AI is no different. So agentic AI is made up of three components: an LLM that can reason, a harness, and tools. And the simplest way to think about this is that the LLM is the brain, the tools are the hands, and the harness is what lets the brain move the hands. And the takeaway line that I always, when I think about agentic AI, is it's an LLM that can take actions. And that's really, really all it is. So we have these individual agents, but they don't necessarily need to work alone. They can work independently, but sometimes they can also work cooperatively in a system. And so depending on the task, depends on how you may want to structure your agentic system. On the right, you can see different configurations of agentic systems. You can see an individual agent, and then you can see different configurations of how they can work together or independently within the system. What system to use depends on the problem you're trying to solve. Similarly, the exact number of agents you need also depends on the task. Normally, a large amount of agents might be particularly useful when you have a task that can be split into smaller pieces or sort of run in parallel. So again, conceptually, what you're thinking of here, you have an LLM that can act, you chain them all together, you break up a task into sort of simple pieces, and then you sort of let them get to it. And there's sort of a framework by Google that summarizes what I've just said of how an agentic problem actually solves the task. So Google has sort of frames this problem-solving loop in 5 stages. The first is perception, which is all about gathering information. Once you've got this information, it needs to reason about it. So that's making sense of all the information that's gathered. It needs to plan, and that's breaking the goal into steps. And these steps might be for individual agents, it might be for a single agent. And then afterwards, once we have this plan, the next step is action. And finally, the sort of final step is reflecting on what the outcome is. And this whole process is iterative. So we continue on this loop until we reach sort of some condition or some satisfactory outcome that's been defined by us as the human. So just a very quick example to help pin this all down. So consider planning a holiday. An LLM alone could generate a holiday plan for you, sort of itinerary and text that you need to act on. A single agent could go a step further and actually book one part of this holiday, say just the flights. A multi-agent system can do the entire thing. So it can book the entire trip for you. It can book flights, it can book accommodation, it could book activities with an iterative loop checking that all these dates sort of line up. So again, you can sort of see an example of this on the right, where you'd have one supervisor agent getting the information from all these individual agents booking certain things, and then repeating the whole process until we have something that works. And then the sort of final slide on this, because this is the thing that everyone's talking about. There are a lot of different uses of agentic systems, but probably the most popular real-world tool, or one of the most popular real-world mature tools at the moment, maybe mature isn't the right word, but one of the most popular tools are coding agents. So these are tools that live in your terminal ID that can directly read your existing code, gather context, and importantly, make edits themselves. So this is different from just copying and pasting an LLM suggested sort of code changes. That's the key distinction with this. The agent makes a change in your code or can actually can actually write code or make changes. And as I mentioned, it's probably one of the most successful and clear applications of agentic AI in the wild. So I've gone through this really quickly, but the main thing I want you to take away from this is that agentic AI isn't a new type of intelligence. It's an existing LLM, which we're all used to, but it has tools and a harness that lets them act instead of just responding. And with that, we reach the end. I'm going to skip through the conclusion slide. Like I said, the slides will be shared. I think the main things that we just want you to take away with is that there's a balance with this technology, and this technology being AI. It's genuinely powerful and useful and improving fast, but it's also really important to consider the sort of costs and ethical considerations throughout it all. And with that, we reach the end of the session. Thank you so much. We will now jump to Q&A. I see that there's a few questions. Like I mentioned, if you have any questions, please post them in the chat. But Gina and I will start answering those that have been asked so far. So I'll start with the first question, which is, in LMIC's context, where local health data are often limited and many LLMs are trained predominantly on data from high-income settings, how can we ensure that these models provide equitable and contextually appropriate recommendations rather than reinforcing existing disparities and biases? I'll have a quick go at answering, and then I'll sort of tag Gina in too. So this is one of the things I mentioned about fine-tuning, and I think Gina also commented on this. It is difficult to prevent this from happening if we're using systems that have been developed, like Gina mentioned, in Silicon Valley, or sort of generated on a whole host of data. So one way to do this is to fine-tune data or fine-tune the models that you use to be more specific to the context that you're working in, or trying to do this from scratch. One of the big issues with this is that it takes a lot of resources to fine-tune these models. So the caveat here is that we need more computational power. We need infrastructure development in LMIC settings, which we obviously know is difficult. So it's trying to figure out that balance and trying to see how we can tweak these models towards specific use cases. Anything to add?
Yeah, I guess just, I suppose, to answer the question in maybe like a simple but also kind of bleak answer, is that like we can't really at the present like time. I think that it's not about necessarily like reinforcing existing biases and things like that. I think it's more about the fact that you just can't 100% trust that the outcome that it's giving you is exactly what you want for your setting, because as we've said, you know, LLMs, they don't know about your setting unless we've told them about it. And as we've pointed out, they may not have known about that. So I think that hopefully through time, that in countries outside of Europe and North America, that these models are going to improve as they get more trained on sort of like local material. But yeah, I think obviously, like you said, they're an incredible tool. So I think it's great for you to use them, and if they assist you in your work, that's fantastic. I think but the main thing is just to always be cautious about the answer that it's giving you, and be aware of the fact that it maybe doesn't understand some of the local nuances that you have to deal with on a day-to-day basis. But obviously, you know that, so you can sort of take it with a pinch of salt. And yeah, I think that's about it.
Yeah, I think the ending point of what Gina mentioned is probably, yeah, the point to hammer home is use it with caution and sort of remember what your context is. And then one more question is it ethical to use LLMs for research writing? I guess the views depend here. In my opinion, for grammar, it's fine, but you can't use it to generate ideas. Like we said, it's been trained across a whole host of different data sources, and it's difficult to attribute where these ideas come from. It might be trained on a different piece of research, or it might be trained on a textbook or something like this. And so you don't know if you're using it to generate ideas or generate thoughts. That's where the problem comes in. But again, pinning down what Gina said, it's very important to look at what comes out and interpret it with caution, and always make sure, if it is editing your text, that your thoughts are actually accurately reflected. So you would be able to tell if sort of it's only changed grammar or something small versus the entire meaning of what you said. And so that's where you have to be very careful with it. Anything to add?
Yeah, I think that I certainly use it, and I think where it helps the best is when, you know, you've got to do something like an abstract or an executive summary or something like that, where you say, I've written this research article, can you just summarize it for me? And I think it's really helpful for things like that. But I guess, as I stated in my bit, it doesn't have an ability to sort of hypothesize or reason. And so when you're in that discussion section of your paper, that kind of does need to come from you, because you obviously have an understanding of the situation in the literature that the LLM just doesn't have. You know, the LLM can churn you out papers, but it has no ability to judge if that's a good paper or a bad paper like you would be able to. So yeah, I think that anything where it has to reason, I think that's where you need to step in and a human is needed. But I think anywhere where you just want to sort of like check your grammar or spelling, like Tristan said, or you want to make a summary of your own thoughts and feelings, and then I think that's kind of totally fine. And it performs well in doing that.
Cool. So there's a bit of, I just need to share the screen again I think I've stopped sharing the slides. Yeah. Gina's just going to share the slides. There are feedback slides. You should see a QR code popping up in a second. So like we mentioned, there is a feedback form to please complete if you do want to receive the certificate, and there'll be a very short quiz to complete at the end of it. If you can scan this QR code and complete the form, I will also share the link in the chat at the moment. I've seen a few people with their hands up. As I mentioned, you can't unmute yourself. So if you have a question, pop it in the chat or pop it ideally in the Q&A panel. A few things to address is that the slides will be shared, the recording will be shared. We will also share the certificates, but that might only be at the end of this week or at some point next week. So just, yeah, it is coming, but you would not have received it as yet. Cool. So I'm just going to pop the link in the chat. So the link is in the chat. Let us know if, yeah, again, with the hands that are up, I haven't seen anything in the Q&A. So we can't really address the questions that you have, but do reach out if you need something. Cool. And I think with that, we're probably close to just on time. There's 3 minutes left, so we'll give you back 3 minutes for your day. We hope you've enjoyed the session, and then hopefully see you tomorrow for the final session in the series. Thank you.
Thank you.